This is a very special subject, right? Quantum mechanics is quite unique in your undergraduate training in the sense that it is the piece of physics it is the great intellectual accomplishment of the last century. It is the piece of physics which is least understood. Relativity and so on is perfectly clear and tied up. Of course, there's a theory of everything or whatever on the frontier of the subject, but here we have a piece of undergraduate physics which it's universally agreed is not properly understood in its deepest underpinnings. It's still fundamentally mysterious, and it's also quite extraordinarily specific to physics, and yet it completely underpins. It's absolutely fundamental. You cannot understand anything about your body, the table, the sun, anything. Everything is a manifestation of quantum mechanics in a very direct way. So it's an extraordinarily exciting subject, and I think what's particularly exciting for you should be that there are pieces of this still to be put in place. There are mysteries here still to be resolved, and I think there's no reason why the person who does that, or people who contribute to doing that, should not be here in the audience today. I don't think it's going to be done by people of my generation. It looks as if it's something that still needs to be done by people coming along with a fresh look at it. So it's extraordinarily worth working out. Physics isn't easy, and quantum mechanics is one of the hard bits of physics. This course isn't easy. But it's extremely well worth working at, and I would stress the importance of working on the problems. There are masses of problems, right? Too many problems. There may be, you will think when you look at the problem sets, which are just some abstract of the problems, there are already too many problems. But it is the way to learn and understand about physics is to work with the apparatus and think about the meaning of the solutions that you get and so on and so forth. And so I really would urge you to work as hard as you can at those problems. And the reason for providing solutions to many of the problems is because you would, even if you can solve the problem yourself, you might find it interesting to see how I solved the problem, and develop your technique in that way. Of course, quantum mechanics has a very funny way of looking at the world. That's part of the problem, and it's by constant practice and experience that you'll deepen that understanding. Okay, so Einstein, as everybody knows, didn't like quantum mechanics. But I think the reason why he didn't like quantum mechanics, which he expressed as God doesn't play dice, was not a good reason. It may be that one shouldn't like quantum mechanics, but that's not a good reason. Let's just think about that for a moment. Physics is about predicting the future. It's about saying what's going to happen. If you lean a ladder up against a wall, you would like to know, if you tread on the ladder, whether it's going to slip and fall down, that kind of thing. And if the data on which we work are always uncertain, and the systems with which we work are never isolated, and our theory, crudely, always applies to something for which we... physics is an apparatus where if you put in certain statements about what the system is, for example, with a ladder, what the roughness of the ground is, what the roughness of the wall is, what the weight of the ladder is, and so on and so forth. If you describe the system accurately, then you will get a precise prediction out. But in the real world, not only can you not, there's always uncertainty in the data. You can't say exactly how rough the floor is, because the roughness of the floor varies from place to place. You're not quite sure where you put down the ladder and so on. So the data that you're working with are uncertain. So what you should really do, the best that you can actually do, if you really want to push yourself to the most precise results, is derive probability distributions. You can say that the probability of the ladder slipping from this position is such and such. The probability of the ladder slipping from that position is such and such. In simple cases, you have a very sharp, you have a very narrow range of probabilities. The probability in certain positions is almost 1 that it won't slip. In other places, it's almost 1 that it will slip. And so we can give a simple answer and we say, well, the critical angle for its slipping is 43 degrees and 34 minutes or whatever else. But if you really, really, really want to know something accurately, if you really want to push your predictions to the extreme, or to as hard as you can, you will have to calculate a probability distribution. And calculating a probability distribution is hard. in classical physics it's hard. And we will find that in quantum mechanics it's actually rather easier to calculate probability distributions with the quantum mechanical apparatus than it is with the classical physical apparatus, which is just as well, because in quantum mechanics we're working on a theory. It arose out of attempts to understand things that are so small that they are always seriously not isolated. So an electron carries a charge. Consequently, it is always in contact with, it's always interacting with the electromagnetic field. But the electromagnetic field is, it turns out, always quivering. So we never know what the electromagnetic field, even under the most precise control of the electromagnetic field. You put your electron inside some resonant cavity, you cool the resonant cavity as close to absolute zero as you can, and so on. No matter how hard you work, it turns out that electromagnetic field is in an unknown configuration. Consequently, your electron is subject to uncertain disturbances. Consequently, what the electron is going to do, the best you can do is predict probabilistically, in the same sense that when the horses are racing at Sandown Park or whatever, the results are going to be probabilistic. You don't know what a particular horse is going to do on a particular day because of all the... It's not an isolated system. It may have eaten something it didn't approve of at breakfast that morning, etc. So it is natural that we should be working with probabilities. It is natural that the calculation... So whereas in classical physics, when you're talking about a cricket ball or a shell shot out of a howitzer, you operate under the fiction, which is a very good fiction, that at every point in the trajectory, at every time, every precisely measured time, the central mass of the shell has a very precise coordinates, and these coordinates progress in a very accurately calculable way. You have only one number to calculate, well, three numbers, I suppose, the x, y, and z coordinates of the shell to calculate it each time. You don't have to calculate a probability distribution. Well, in the simple case, you don't. If you're considering what will happen when an electron leaves an electron gun, because of the quivering electromagnetic field, whatever uncertainty there was in the configuration of the electron before it shot out of the gun and so on, it's inevitable that you're calculating a probability distribution for where the electron is going to go. And calculating a probability distribution for every possible value of x is clearly going to be a hell of a lot more work than calculating one particular value of x, right? So that's why it's going to be mathematically complex and why it's going to involve probabilities. And let's just remind ourselves of some basic facts about probabilities, which I think, is this correct that in Professor Blundell's course he's already talked about the laws of probability? Yeah, good. So the things we need to just remind ourselves of is that if we've got two independent events, the probability that we get the event A and the event B is going to be the product of PA and PB. So we multiply the probabilities of independent events, such as that if you throw two dice, the probability that one die comes up with number 1 and the other one comes up with number 6. So PA might be the probability that the first die, the red one, comes up with number 1, and PB might be the probability the black die comes up with a number 6. Then this is the probability that the red one comes up with 1, what did I say, 6, whatever. This is the probability of that particular configuration, and you get a product. And the other rule that's important for us is that the probability of A or B is equal to PA plus PB if they're exclusive events. So that's the probability that if I throw a single die that I get either a 1 or a 6, because I can't get both a 1 and a 6 simultaneously. I either get a 1 or I get a 6, so these are exclusive events. And the probability that I get either a 1 or a 6 is just the sum of these two probabilities. So those are the... And following on from that, if we have x is a random variable, so that's something like what happens when we, like the number we get when we throw a die, then we define a thing called the expectation of x. to be the sum of the probability of the ith outcome times the value that x takes on the ith outcome. And it's sort of, roughly speaking, it's often called the average of x, but that is to say, if you make a number n of trials and work out the average value that you get of x, you're hoping to get a value, you should get a value which is close to this. It will never really agree with this. But the idea is that as you do more and more experiments, the average of all those experiments will converge will rattle in a narrower and narrower range around this expectation value. And we have a few simple rules that if we have two random variables and add their results and then take the expectation value, then that is the expectation value of x plus the expectation value of y. That's always the case, whether the the variables are independent or not. So, and zillions of branches of science use probabilities, right? It's a major feature in medicine, major feature in the financial markets, and they use probabilities in just the same way that physicists do. But physicists have a unique way of calculating probabilities which nobody else uses, and I think this is a central mystery. And that's because in quantum mechanics, we calculate these probabilities through amplitudes. That's to say, every probability that we're interested in, P, is the mod square of some complex number. It's amplitude. It's probability amplitude. So we never calculate this directly. We always calculate a probability amplitude, and having got it, we take its mod, which is a complex number, and we interpret the mod square of that complex number as the probability. And so all of quantum, my purpose in the next few lectures is to persuade you that all of quantum mechanics and all its strangeness follows from this business here, which nobody else uses. There's no other branch of knowledge. You know, there are people in the city who talk about the quantum mechanical. There are even people who name their hedge funds quantum, etc. They like to have a connection with quantum mechanics, but it's completely bogus because they never calculate probabilities in this way. Okay, now the consequence of this is that the probability of supposing something can happen by two routes, right? So let's be specific. Let's suppose that we have an electron gun, and we have a double slit arrangement. Whoops, my drawings are never very good. Something like this. And we're firing electrons out of here, sort of in scatter pattern, and some of them go through holes and then hit our detector, our screen over here, scintillator, photographic plate, whatever you want to use, and others bounce, oops, and then, so we'll call this S and we'll call this T. There are two, if we focus on a particular place, X, here on the screen, there are two ways in which an electron can arrive there. It can go through the top hole or the bottom hole. And we'll call the path through the top hole the path S, and the path through the bottom hole the path T. So what we're interested in calculating is the probability that we get an electron arriving at X. So the probability of arriving at X should be calculated from some amplitude, and the rule is that amplitude is the amplitude to take the path S plus the amplitude to take the path T. And then, of course, that gives us the amplitude to arrive there regardless, right? So this is like the probability rule up there, P, A, or B. This is the probability that it got there by either route S or route T. Is the sum, well up there it's the sum of two probabilities, but the rule here is that it's the sum of, the amplitude for it is the sum of the amplitudes, and the probability is the square of this. And what does that give us? That gives us, because we know how to take the mod square of the sum of two complex numbers, this is AS mod squared plus AT mod squared plus AS AT complex conjugate plus AS complex conjugate AT. So that stuff follows just from the ordinary rules for taking the amplitude of sum of two complex numbers. But this we know is the probability that it got there through S. So that's P that it took root S plus P that it took root T plus this stuff, which can be, this stuff here can be written as twice the real part of AS A star T. So the probability that something happens when it can happen in two mutually exclusive ways, because it either goes through the top hole or it goes through the bottom hole, is the probability that it is the sum of the probabilities that it took either root plus this funny stuff down here. That's a consequence of calculating probabilities using amplitudes and this fundamental principle that if something can happen by this way or by that way, then you add the amplitudes, you don't add the probabilities. Nobody knows why that's the right rule. You should reasonably ask me, so how do I know that's the right rule? And the answer, I think the proper answer to that question is that this is the fundamental cornerstone of quantum mechanics, and our civilization quite simply depends on quantum mechanics because we're all busy communicating with each other using electronics that has been designed using quantum mechanics. So it's, of course, there are particular specific experiments that one could talk about, but really it's not as persuasive as the point that without this, quantum mechanics would make no sense, and without quantum mechanics, our civilization would fall apart. Now so let's think a little bit more about this. What do we think that these individual probability distributions look like? In other words, if you covered up one of these things and were just firing your bullets through one hole, what would you imagine? Well, of course, your electrons, your bullets, your particles through one hole. What we would imagine was that the majority, that the probability would be largest on the place which was formed by a straight line from the center of the muzzle of the gun through the hole to the screen. So you would expect that PS look like, so I want to draw a plot of, this is going to be X. I guess I better put, this is X is naught. I would expect that PS looks something like this, some kind of vaguely Gaussian, so it's most likely to arrive, this is the point which is the geometrical, is the intersection of the straight line through the middle of the muzzle and the middle of the hole, right? And there's some width, because the slit has some width, the muzzle has some width and doesn't fire bullets exactly in one direction, but in some spray of directions. And we would expect that P of T correspondingly was the same thing on the other side of the origin, right? So if these Gaussians are very narrow, we're expecting that P of X at some location here, say, if we chose this place, we'd find that P of T was about equal to 0. P of S, PS was sort of some number here. So this vanished. This amplitude would vanish because this is the mod square of whatever complex number it is that sits underneath. And so this term would disappear, and we would find, guess what, surprise, surprise, that the probability of arriving at X was indeed equal to the probability of arriving through S. But suppose these things, and now we're interested in the more interesting case where these are really broad distributions. And this is a really broad distribution. Whoops. But really broad distribution. Okay. Then there will be places where there's a non-negligible amplitude coming from both sides. And in fact, by symmetry, it's evident that at the origin, in the geometrical middle of the screen, there will be equal amplitudes coming from the equal probabilities expected from both sides. So in this neighborhood, we're expecting that, that this number is about equal to this number, and these two numbers have comparable magnitudes. So let's, in fact, write A of S is equal to mod A. Let me put a subscript on it. Mod A S e to the I phi s. Okay, so this is a complex number. That's the funny quantum mechanical thing. So it has an amplitude in the technical sense of, this is a quantum amplitude, but it has an amplitude in the sense of complex numbers, a modulus sitting in front here, and then it must have some phase up there. Similarly, we'll write that AT is equal to AT e to the I phi t, and both and everything here will be a function of position down on the screen, right? This amplitude depends on where you are on the screen, and this does, and we expect that this does. We expect all of these bits of the complex number depend on position. But when we're in the middle here, so near center of screen, we're expecting that the modulus of AS is about equal to the modulus of AT, because this is the square root of the probability of getting there, and this is the square root of the probability of getting there, this through S only, this through T only, and we can't see any difference between the two. So what does the combined probability look like? Then P of X is on the order of, it's about equal to 2 times the probability of getting through, through S, because PT is about equal to PS. But now we're going to have plus twice, we're going to have AS mod squared. No. Right? Because we're saying that up there we've got A of S times A star T, but we're saying that the modulus of AS is about equal to the modulus of AT, so I can just put in that product just becomes this times e to the I, times the real part of e to the I phi s minus phi t. But this we recognize as the probability PS. So this is about equal to 2 PS 1 plus, and the real part of this, of course, is the cosine of phi s minus phi t. So this is what we're expecting. It's only an approximate relation, and it's only valued near the middle. But the conclusion of this, the implication of this rule for adding the amplitudes is that the probability as a function of position near the center is going to be what you would naively expect. So this is the classical result, right? The classical result is the probability of arriving there is twice the probability of getting there through either one of the slits, because each slit's contributing the same probability. But this is now being multiplied by 1 plus cosine of this totally quantum mechanical bit. And this bit is called the quantum interference term. And so the prediction is, since this cosine, so this difference, we'll calculate what this difference between the phases is later on. We can't put a number on it at the moment, but we do expect phi s and phi t to be functions of position. And so by default, we have to expect that this thing is varying with position. And as the argument of the cosine varies with position through, goes through 0 and 2 pi and so on, the cosine is going to go from 1 to -1, and this probability of arrival is going to go from nothing to twice the classical probability, 4 times PS. So what we're expecting is that at the end of the day, P of x is going to do some kind of oscillation. This is only valid in a small region of x, but it is an unexpected. It is surely a surprising result. So this is 2 times classical probability, and this is 0. So that's phenomenon of quantum interference is an inevitable consequence of this extraordinary rule for adding amplitudes and calculating probabilities from the sum of the amplitudes rather than adding the probabilities. That is what makes quantum mechanics special, and that is a phenomenon which nobody else who uses probability encounters the need to do this. Only physicists encounter this need. That, I think, is the real mystery. How are we doing? Okay. Of course, we have to ask, why is it that if you fire machine gun bullets through slits and stuff, we're not expecting to find that there's a safe place to stand every yard or every millimeter or any distance. These places where no machine gun bullets are going to arrive, we don't believe exist. And you have to ask the question, why not? And the answer, we will calculate the answer later on, but the answer is going to be that as the mass of the particles you're firing goes up from the mass of an electron up to the mass of a bullet, this pattern stays the same, but it gets more and more and more and more compressed. In other words, this distance between places where it's safe to stand gets smaller and smaller and smaller and smaller until it becomes ludicrously small in the case of machine gun bullets. And when you make any measurement with machine gun bullets, you inevitably average over the places where the bullets are extremely likely to arise, twice as likely to arise as in classical physics, and the places where it's safe to stand. So you inevitably average over these places, and you end up with this average. You're unable to measure anything but this average. Nobody has figured out a way to measure anything but this average in the case of things like machine gun bullets. So that's how we recover classical physics. But quantum mechanics is asserting that there really are these places where it is safe to stand, if you were small enough. Okay, so now let's talk about quantum states. So my claim is that essentially everything follows from what we've already covered, that it's all a consequence of this interference business through using probability amplitudes instead of probabilities. But now we have to have some apparatus. So we have got we have in our lab some system, something that we're trying to investigate. So in the simplest case, it would be a particle, a spinless particle, and let's fantasize about spinless particles. So that's particles which do not have any, that aren't gyros. And let's fantasize about them, although it turns out that spinless particles are very rare, and things like electrons and neutrons and protons even are little gyros. So if we had a spinless particle, it's a system, it's a dynamical system, and you can ask yourself, so how do I characterize the state of this particle? Well, there are things you characterize its state, of course, by measuring something. And what can you measure? You can measure the x, y, and z coordinates. You can measure the px, py, and pz momenta. You could measure its energy. You could measure its angular momentum. These are all things that you could measure. So there's a range of things that you could measure, and in quantum mechanics, these things you could measure are all called observables. Then you characterize the system by saying what results you would get if you made these measurements. Now, in quantum mechanics, remember, we've accepted that there's a probabilistic aspect, so we don't expect to be able to say that if I measure x, I will get the value 3.1415963, whatever, right, meters. I expect to have to come clean and say, well, I don't know, there's a probability distribution. I think it's about round here. That's just how life is going to be. So what do you do? What you do, of course, is you specify the quantum amplitudes to obtain certain results of measurements. So we characterize the system, the state of our system, by measuring, by giving quantum amplitudes to possible outcomes of measurements. Outcomes. I think that's pretty reasonable. And it turns out in quantum mechanics that the possible outcomes are sometimes, but not always, restricted. So if you have an electron which is free to wander the universe, then the possible outcomes of its x-coordinate can be values from -infinity to +infinity. All real numbers are on. And the range of possible values are what are called the spectrum. So the possible outcomes the numbers you can get they form the spectrum. So the spectrum observable. So the spectrum of X is generally -infinity to infinity, which is not a very interesting, so there's no interesting restriction there. Similarly, the spectrum of Px, the momentum in the x direction, is usually the same. But the spectrum, for example, of the z component of angular momentum, Jz, turns out to be only discrete values. It turns out that we'll show that this is the case, that you can have numbers like ... comma, k minus 1, h bar, k, h bar, k plus 1, h bar, k plus 2 h bar, and so on, where k is equal to either, for a particular particle, it's either equal to 0 or it's equal to a half. So the spectrum can be discrete set of numbers, or it can be a continuous set of numbers. This is a property of the observable. The spectrum of the energy is often a discrete set of numbers, not always E0, E1, E2, that you have to calculate by hard grind, and we'll spend a great deal of time calculating the spectrum of H. It turns out to be a key to find out what that is for a particular system. So all these observables have spectra, and how you would characterize the state of the system if you were talking about its energy is you would give the amplitude. So we could possibly specify the state of our system by giving the amplitude to get E0, the lowest energy, the amplitude to get the next energy above, the amplitude, etc. So let's call this A0, A1, etc. So the idea here is that for some systems, if you know the complex number A0, whose mod square gives you the probability of, if you would measure the energy, that you got the possible value E0, and you also knew this number, A1, whose mod square is this probability, and if you knew this number, whose mod square was the probability of getting the nth energy level, and so on, right? In general, there'll be an infinite number of these. If you knew all of these amplitudes, you would completely know, you would have completely specified the dynamical state of that system. What do I mean by that? What I mean by that is, if I knew all of those amplitudes, I could calculate the amplitude to find any other amplitude that you might inquire about. For example, I could find the amplitude to find my system at the place X. Or I could calculate, from those amplitudes, I could calculate the amplitude to find that the momentum is the value P. So we have the concept here of a set of amplitudes. It's clear, I hope it's clear, that you will need a set of amplitudes to define the state of a system in quantum mechanics. In classical mechanics, what do you need to know? You need to know, for a particle, you need to know x and p. X and px, x, y, and z, and px, py, and pz, because then you've pinned down where the thing is and how fast it's moving. And when you know that, you're all done. 6 numbers, done. Because from that, you could calculate the energy, you could calculate the angular momentum, done. But in quantum mechanics, life isn't going to be so simple, because we've agreed that you probably don't know what x is, and you probably don't know what px is. The best you can hope to know is what these probability distributions are. And we've agreed that these probability distributions are, for reasons that nobody understands, going to be defined in terms of these complex numbers, the quantum amplitudes whose mod square give the probabilities. So specifying a complete set of information is a matter of writing down a long list, unfortunately, of quantum amplitudes. The good news is that you don't need to know you don't need to write down all possible amplitudes, quantum amplitudes, because there are rules which we're going to develop for calculating from a complete set of quantum amplitudes all other quantum amplitudes that might be of interest. And we'll do a concrete example probably next time. Maybe we do have time to just do this. Yeah, okay, so let's have a look at this. So I said that electrons and protons and neutrons and quarks, a huge number of elementary particles have gyros. So they have an intrinsic spin. They are gyroscopes, they have an intrinsic spin. And they're called spin-half particles for reasons that will become apparent in a moment. Let's just use this. We'll develop the theory of this properly next term, but I want to use this as an example of a complete set of amplitudes and what it enables you to do. Okay. So the total angular momentum of these particles is always the same. They spin at a certain rate so that they have an angular momentum that's root 3/4 of h bar, where h bar is Planck's constant over 2 pi. So that's the amount of spin they have, and they just have that spin, and you can never change it. It's always the same. But what does happen is that the direction that this angular momentum points in changes. So whereas the total angular momentum is this, the angular momentum in some particular direction, for example, the z direction, if you measure it, it turns out that you can only get 2 answers, plus or minus a half of h bar. So, and moreover, there is an amplitude, A plus, so let this be the amplitude to measure Jz equals a plus a half h bar. And obviously A minus will be the amplitude to measure that Jz is minus a half h bar. Now, in ordinary talk, what we say is, what everybody says, and you'll find me saying this, but it's immoral, I shouldn't, is that if Jz is plus a half h bar, its spin is pointing upwards, and you imagine it to be a little particle doing upwards. And when Jz is minus a half h bar, you say it's pointing downwards. Now, this is a fundamental mistake, because if you square a half h bar, and take the square root, you don't get that, right? This 3 indicates that actually this particle has a quarter of h bar, sorry, it has a half h bar associated with the x and y directions as well. So it's actually not a good idea to think of it as spin up, as being having a spin pointing upwards. The most that we can say is that really it's pointing sort of not downwards, it's pointing vaguely up, and this one is pointing vaguely down. I don't really know which way it is in the xy plane. So that's just a little word of caution. People get themselves into a real tangle by imagining that this means the spin is up and that means the spin is down. We all say that, and you'll find me saying that, but just when you find yourself saying that, just have a little trip in the brain which says, hang on a moment, I mustn't take that too literally, because it does have angular momentum in the x and y directions, even though I've measured Jz and found it up in Jz, or Jz and I found it down. Okay, so the good news is that the set A plus, comma, A minus is a complete set of amplitudes. What do I mean by that? What that means is, if I know those two complex numbers, if I know both of those two complex numbers, I can calculate the amplitude and therefore the probability to find the particle with its spin in any direction that I want, that you specify, is either plus a half h bar in that direction or minus a half h bar in that direction. And we'll work that out in some detail. Yeah, so from these, we will, maybe I want to write the formula down, I'm not sure. Moment with the notes. No, I don't think we do yet. We're not ready to write that down. We just want to make that statement that that it's a complete set of amplitudes in the sense that we will derive rules such that we can calculate B plus, which is a function of A plus and A minus, which is and this is the amplitude to measure J in some direction theta to be and the theory consists, so what the theory of quantum mechanics is about, it's about finding the rules which enable you to calculate the amplitude for an event that you want to know what's the probability of something happening given your current state of information, which is a complete set of amplitudes down here, a complete set of amplitudes for something else to happen. That's what the apparatus consists of and is there to do. So I think that it probably is an appropriate moment to stop, because the next section requires a bit of space, which we shouldn't take now.